All right, so good afternoon, everyone. We will begin this workshop, and my name is Andrea Polidori. I am the Advanced Monitoring Technologies Manager for the South Coast AQMD, and one of the lead for this project. And so I would like to welcome you, and would like to thank you for your interest in this project. And it's really exciting to have citizen scientists and members of the public that are more and more interested in learning more about air pollutions and about what we do at the South Coast AQMD. So thank you for, in advance for your participation. And today you will learn a lot more about the project and, specifically about these low-cost sensors for monitoring particulate matter and for monitoring air quality. And, you will learn, what they do, what they don't do, and how to operate them and how to use these sensors to gather useful information, not just for this project, but also, to learn more about the air quality conditions, where you live. I have several of my staff here, including one of my supervisor, Olga Pikelnaya, and Vasilios Papapostolous. As you can notice, the names, first and last name, are pretty difficult to pronounce. Maybe it's the most difficult thing today about this workshop, but you'll get familiar with everything, including the names. So without further ado, I would like to introduce Olga, that will tell you more about the project. Unfortunately, I have two events that are going on at the same time, so I'll be here for the introduction, of course, and later on when we have the discussion about the sensors and about the project. So thank you again.
Good afternoon, everyone. Thank you for coming and spending your Friday afternoon with us. So I'm just going to run really quickly about the safety situation here. So in the event that we have to evacuate the room, we have two exits, one behind me and one behind you. And in the event of the earthquake, duck and cover. And the bathrooms are, if you go out of the door behind you and then out of the next door and turn left, the bathrooms are right there. So I wanted to echo Andrea that, I wanted to welcome you to this workshop, and I've communicated with some of you over the phone, over the email, and again, we really appreciate your participation. You are the center for this project. Without you, this project would not happen. You see the agenda here on the screen, that just kind of to guide us through what's going to happen during this workshop. And I'm going to turn my microphone to Pavan Gupta from NASA Goddard, who is also one of the co-investigators for this project. And he will tell you a little bit about, just to give you an overview of the project and why we're doing this experiment in the first place.
Thank you, Olga. So there are empty tables here. Can I request everyone if you can come in the front so that it will be easier to talking? The last bench, can you come in the front, please? If you don't mind, please. It will be easier to discuss things. So again, my name is Pawan Gupta. I work at NASA Marshall Space Flight Center in Huntsville, Alabama. And I will give you a very brief overview about the project. But before that, I think it will be a good idea to, if you can introduce each of us and tell why we are here. So let me start with maybe here.
Hey, Vasilios Papapostolou. I'm the program supervisor of the AQSpec program of the South Coast AQMD.
Hi, Brandon Feenstra, and also work in the Air Quality Sensor Performance Evaluation Center at South Coast AQMD.
I'm Chuck Ritz. I'm retired from Cal Poly Pomona and just interested in being a citizen scientist.
I'm Jennifer Nguyen. I'm the AQMD inspector for Reclaim.
I'm Xiang. I'm air quality specialist working in the air quality assessment group.
And I'm in air quality assessment group 2 planning.
Sam Atwood, interested in air quality technology and AQMD retiree.
Kim White, AQMD Media Office, Senior PIS.
Hi, my name is Carolina, and I'm part of Olga's group here at South Coast AQMD.
My name is Ashley, and I work in the AQ Spec group here at South Coast AQMD.
Olga again. I am a co-I of this for this investigation, and I'm also program supervisor of the optical remote sensing group here at AQMD.
Hi, I'm Ross Chung, air quality specialist here at the South Coast AQMD.
My name is Brittany Gallivan, and I'm an air quality specialist here at AQMD in the Planning, Climate, Energy, Policy Incentives Group.
Yes, hi, my name is Al Baez. I'm program supervisor of the Best Available Control Technology Group, and I have one of these purple air devices at my house, and I'm here to learn more about it.
I'm Mark Carreras, also at AQMD doing air quality modeling, and also I have a purple air sensor.
I'm Fan Xu. I'm in the Technology Advancements Office here at AQMD. I also have the purple air device at my home. Yeah.
I'm Trey. I'm working at a modeling group planning, South Coast AQMD.
I'm Sagar. I'm a chemist here at AQMD.
Good afternoon. Mike Dro from the Claremont area, citizen scientist, I guess, with a purple air device, and want to find out more about what it's doing.
Hello, my name is Ivan Ruivar, and I work with the South Coast AQMD Advanced Monitoring Technologies Group.
Hello, I'm Victoria Reiser, and I'm going to be a citizen scientist. I'm a school nurse, so I don't know anything about this, but I'm looking forward to it.
Hi, my name is Marco. Also, I do not work for AQMD, representing Claremont myself as well. Just want to learn more about this. Looked interesting, so here I am.
Do you have sensor already?
Pardon me? Yes, I do.
Okay, great.
Hello, everyone. My name is Victor Polanco, and I work for the Coalition for Clean Air. And I do some installations of the air quality monitor, Purple Air, and I'm here to learn more about the data analysis tools.
Hello, my name's Harvey Etter. I'm with the Public Solar Power Coalition and coming to the district since '85 and doing solar, immediate total solar conversion equitably and justly, etc.
My name is Mike Stein. I'm from Santa Clarita. My wife works for JPL, and so she gave me the information on this, and so I'm here.
I think there is one more person. Just get me. I don't know what the question is. Just introduce yourself and why you're here.
I'm April, and I thought I snuck past this question, but I'm here because I like the idea of the program, and I have lung disease, so I'm very interested in air quality.
Thank you. So can you, means a lot of people says they have either air quality sensor or either on their home or they received and they're planning to install. How many people are going to have? Do you have already it? Yeah. Okay, and you plan, or who have planned to install at their home? Do you have, ma'am? Have you registered for it? Okay, so you should be receiving one, right? Okay, great. So we learn, we have these sensors over here, and Brandon is going to show how they works and what we can do with that. There are data tools which you can use to look some of the data and check your quality. So I hear a lot of people are from AQMD here, so I don't have to tell them why we want to measure air quality, and because if they don't know, it means you're at the wrong place. So, but it's still for the sake of completion and few new people I see, just give you briefly what we are going to do. So this project is funded from the NASA. It's called Air Quality Citizen Science Project. And the idea is how we can make more awareness among citizen scientists and communities who can help us to collect some of the ground data using this low-cost sensor, which will help improve NASA's satellite observation of air quality. So it's a kind of a joint program where NASA scientists involved with the AQMD, and the PI is from RTI Research Triangle Institute, Dr. Prakash Doraswamy, and his colleagues over there, myself and Robert Levy is at NASA, and then we have Andrea, Olga, and Brandon who are helping with this project, and they are on this project from the AQMD. So it's a multi-institutions collaborative project funded for actually 4 years. In phase 1, we did for 1 year, and now we have 3 more years to work with on this thing. So I'll just give you a brief overview of that. So before going into details, again, very quickly, most people knows that this is from the World Health Organization report, about 90% populations around the world lives in areas where their quality is not breathable or doesn't follow the WHO guidelines. And we can often see this pollution coming from different sources, either originating on the ground, and you can either smell the pollution, or you see it from your eyes, or you can feel it through your when you breathe. So, but these are only from the ground. So now the pollutions are mainly two different categories. One is gaseous pollution, and one is particle pollution. So in today's workshop, we are mostly going to focus on particle pollution or particulate matter, or in climate community they call aerosols. So these are the particles suspended in the air, which actually we breathe along with the air, and they are very small, tiny particles. So this sensor which you have at your home, or you are installing, or which are sitting here, make measurement of these particles. It's PM 2.5. And if you want to compare the size of this PM 2.5, how small this PM 2.5 in micrometer, then you can compare with the human hair. Human hair is about typically 60 to 70 micrometer in a diameter, so you can assume it's a really tiny, tiny particle, which often we cannot see from our naked eyes. There are other comparison for PM10, PM1 is also monitored for certain applications, but I'm not going to get into those details here. So what we do, once we make measurement of these particles, depending on their value, concentration in microgram per cubic meter, how much concentration in volume of a 1 cubic meter air is there, those numbers are converted in something called air quality index, and these are defined by US EPA. Each country have their own definition of this air quality index, and there is a global also. So US EPA defined that, and these are the most recent based on a 24-hour mean values. And once they are calculated air quality index, those are converted into something called air quality categories, and those are color coded in a way that public can understand. So green means good, moderate means it's mostly good, but it can be unhealthy for certain group of people. And then other categories is started where air quality can be unhealthy. So each of these colors are associated with some kind of advisory or health impacts. And again, those are based on research studies. Again, EPA defines them and put out as a warning for the public. Okay, so let's get into more details about this project. So typically we make measurement for regulatory purpose. That's what AQMD does, US EPA does, using a reference method. And these reference methods, the instruments can cost actually the cost of instrument plus maintaining it and monitoring it for long term. It can cost about 100,000 per year. And then we are trying now in last 10, 15 years, we started using satellite data to see if we can exploit the satellite data to monitor air quality, not just in the US or in California, but all around the world, because satellite does give you global observations. And then in last 5-10 years, we have this really lot of companies putting together low-cost sensors, and one of them is here, which we are trying to use here. And these low-cost sensors does provide same measurement as reference method in terms of the parameter quantity, but there are lot of differences because of the quality of the instrument, so the data quality may not be the same as what you get from the reference method. So these are like $250 instrument compared to $100,000 instrument. So you can compare but the idea is how we can make them better and how we can use them in a way which can help us. So this project, one of the goal is to actually test these sensors and see what kind of data quality we are getting. The other goal is how we can motivate individual citizen scientists to use this data along with the satellite data to be aware about their quality in their own communities, regions. And then the third is how can we use these sensors in large numbers all around the world so that we can actually get some information, some quantitative information, which will help us to improve satellite data quality. Again, idea is to do this on a global scale, not only on a smaller scale. So and then there are other science questions, which I'm not going to go into detail, but again, all of those are tied up with upcoming satellite missions specifically designed for air quality and how these low-cost sensors can play a role either in validating or improving those data or making them information better available to the public. So this is our overall project. We did a phase 1 for 1 year in which we deployed about 40-50 sensors in California, in this region actually. AQMD helped us to deploy all those sensors. And then we did some research studies. We evaluated the sensor quality. We integrate the data with the satellite. And we have some reports and publication out of that. And now this is the phase 2 in which we are going to deploy in 3 different locations. One is California. Again, we are expanding the network here, putting more and more sensors. You will see a map in recently. And then we are actually going to a very kind of relatively clean condition in Raleigh, North Carolina area, which is relatively very clean. So we want to sample the air in 3 different locations. One is really clean. Los Angeles, this area is moderately clean. And then there is in Delhi, in India, which is really super polluted area. So we want to see how this sensor performs under different mass concentration of PM2.5 or different air quality conditions. And that also will help us to understand the satellite data as well. So again, these are just showing some results from the phase 1 study. We had a workshop here. Those are the location of the sensor which we put in California, and on the left there are some results. So in general, we found that most of those, the top left plot is showing basically a comparison of this low-cost sensors with the reference monitors. So in general, they pick up the diurnal variability and the trend very well, but there are offsets in terms of the absolute values, which we have to be aware, and we must calibrate that when we are using for scientific research. Similarly, for the bottom left plot, we are trying to show that satellite data and the low-cost census data kind of shows similar information. This is a case study which we performed during a fires in Bay Area in San Francisco, which was happened in 2016, I believe, October 2016. And we tracked the pollution and the smoke coming out from those fires, both from the satellite and from these low-cost sensors, and we found a lot of similarities between the 2 measurements. So it kind of gives us another justification of using the satellite data for air quality monitoring. So there are a lot of questions which we want during this workshop, so we'll discuss throughout the next 2-3 hours. And basically, some of you already have installed, some of you are in process of installing instrument. So we want to get a lot of feedback from you whenever you, either it is during the installation or if you ever happens to look the data on the map, on the purple layer. I will show you some of the satellite tools where you can actually look satellite imageries in your areas or around your areas, and you can probably compare what your purple layer sensor is showing and what satellite is showing, and they are very easy to use tools. And if you happens to do anything with the data, we will love to hear about that. Please send us email, Olga's email. You must have, all of you, any pictures or any specific events you noticed. You did a barbecue in your backyard and see a peak in your, or there was a fire happening nearby and you see something on your sensors. We would like to know that if you happens to notice that. So we want to make sure that you are engaged throughout the projects, and we can take all those feedbacks and questions from you, and then so that it helps us to understand overall how we can do this more in futures. Okay, I think that's all I have. This is the website, project website. So we have a lot of materials there. All the material which is going to be presented today will be posted there. You can access that. All the peoples who are involved in the projects, their contact information is also there. So if you need to contact any of us, feel free to email us. I think that's all. Yes, sir.
On the scale, we had, I want to know. Hi, hello. My name is Harvey Etter. I'm with the Public Solar Power Coalition. On the scale, you started like 0 to 50 is good. What are we measuring? 0 to 50, what units? Because I've heard that's only for PM recently.
Sure. Brendan, can you go back to that slide? Okay, so what this sensor and EPA and AQMD standard monitor make measurement of is called PM 2.5. Particulate matters are the particles which are smaller than 2.5 micrometer in aerodynamic diameter. So that's their dry mass, and those values are shown on the last column. And they are measured every 1 hour, but when you calculate the air quality index, they're averaged for 24 hours. So it's 24-hour average values, and those are given in microgram per cubic meter. So it's a mass concentration. Now, once you take those values, those are actually converted into another values called air quality index. And if you see, they are linearly scaled. So you just rescale 0 to 12 between 0 to 50. And they are designed not only to do PM 2.5, but EPA monitor like 6 different pollutant criterion. And you can combine them actually and calculate one single air quality index out of multiple air quality criteria. And that can be converted into air quality category, which defines the color. So that 0 to 50 has no unit, in other words. It's just number defining, which was rescaled from 0 to 12. It's just for easier to understand.
I'm interested in the interface with the law, where in body count, social costs, like if they say $9 million per premature death attributed to PM, they say there's 44,000 a year in the district, 7,500 in the state.
Yeah, Olga, you want to comment on this? Is more like local question.
Yeah, so I mean, this project will not answer this question. You know, this is specifically, you know, for measuring the PM and also for like helping NASA to understand better how to refine their satellite measurements, and perhaps in the future, the satellite measurements will be able to answer this type of question. Yeah, and we can talk a little bit more during the break. Yeah, so I think we're also running a little bit behind schedule. So.
We'll be around during the break, so if you have more questions.
Hi, my name is Brandon, and I'm going to talk to you guys today kind of an overview of the Purple Air sensor, which is a sensor that we are using in this project, and then as well kind of do a run through of the Purple Air website so you can get a feel for how that works. We'll look a little bit at some siting considerations for when you guys install these sensors, and then instructions for installing, configuring, and registering the sensor, and then as well look at that Purple Air map. Real quickly, can we have everybody who has received a sensor raise their hand? All right, keep it up. Everybody that has configured or installed their sensor, configured it to Wi-Fi, and registered it and has seen data on the Purple Air map. All right, good. So we'll run through this. Some of you have already seen it. Just to kind of give you a background of typical ambient air quality monitoring, the South Coast Air Quality Management District has about 40 stations here in the South Coast Air Basin. And the purpose of this is to look at the regional attainment of the national ambient air quality standards. The map shown here can be found on our website. And this is done through a network of high-cost instrumentation and a monitoring group that goes and visits those sites, maintains and calibrates that instrumentation. The air monitoring stations look like this. They're large, they can be bulky, they take up a bit of real estate, and it takes a team of people to keep these things calibrated, running. But the end result is that we get high quality data, and we're able to determine whether or not that region is meeting attainment of those national ambient air quality standards. The cost for one of those stations can be upwards of $100,000 to $200,000, and that cost can increase dramatically if you, with specialty instrumentation that gets put in one of those stations. So it definitely depends on what kind of instruments you're outfitting that station with. This project is kind of transitioning as low-cost air quality sensor technology is coming out from that regional scale monitoring more to a local scale, and that's where we come in with the citizen scientist. This is the Purple Air PA2 sensor, and the size of it is small. You guys have seen it, you've received it, and what comes in the box is the Purple Air sensor. It has two sensors actually inside. So it has an A and a B sensor if you look at the far right image. Also has an outdoor rated power supply. When you install that, make sure it's off the ground so it's not going to be getting wet or away from sprinklers. And then it's going to come with some mounting hardware, some screws or zip ties for mounting it either to the inside of an eave or zip tying it to a fence post or something along those lines. The sensor measures 3 different fractions of particulate matter, PM10, 2.5, and PM1. And it also measures pressure, temperature, and humidity. The sensor has 2 requirements. To get it installed, it needs power and accessible Wi-Fi. And the estimated cost is $230, and for participating in the project, we're providing it to you free of cost. As mentioned before, we have the AQ-SPEC program at South Coast AQMD. And this program evaluates the performance of low-cost sensors. So it acquires sensors in triplicate and it evaluates them at an ambient air monitoring station, deploys it just like a citizen scientist would, except for we have the high-cost instrumentation there, and then we can compare it over a 2-month time period and see how well that device performs. All those results are publicly available on our AQ-SPEC website, and you can see that at the top of this slide. This is one of the reports that we have on the Purple Air sensor, highlighting the performance of that sensor both in field evaluation and in laboratory evaluation results. We also have a specific field report and a laboratory report that can be found on our website. So the 3 main steps to install your sensor is installation, Wi-Fi configuration, and registration. And you can put the installation as number 3 if you want to, because you can do the Wi-Fi configuration next to your hotspot or your Wi-Fi router sometimes to make it easier, depending on where your final install location is. If it's far away from the router, you may want to do it inside the room where you have your Wi-Fi router. So quickly on siting, where should I put this sensor at my home? There's a lot of different locations it can go. We want to stay away from sources of air pollution at your home. Keep away from your barbecue. Keep away from your air conditioning unit or vents from your kitchen. Here's a picture of a sensor that's mounted on the outside of a fence that's on the top of a deck. And you can see that that sensor has a view out towards the backyard of that property, so it has kind of a 180 view out, and so it has a good flow of air coming to it. We have another example here on the far right-hand side as well. That one's mounted on the outside. That could be mounted on the inside as well if you wanted to keep it more in the shade. We recommend that you find more of a shady spot for the sensor, so then the temperature readings will be a little bit more accurate. Here's another example of a sensor that's been sited on top of a roof, and you can see that the roof even has a raised edge, and as well it's mounted right next to an AC, about 2 inches from the top of that roof. So this is something you don't want to do, is mount it like that. You're not going to get air quality readings that are representative of the area that it's displaying. Do we have any questions on siting now as we're kind of discussing? Yes? Yeah, so you typically want to be about 15 to 20 feet away from your barbecue. Typically, it's hot air, so it's going to rise. So as long as you get that distance, you should be fine. Yes? Yeah, so the question was, there's a neighbor that has a dryer that's running and it can be smelled in the air. Anything further on the question? Yeah, that should be fine. It may pick up some of the particles from the kind of the lint that's going up. It's hard to say. Maybe you could put it on a different side of your house, but if that's the only location that you have, go ahead and install it there. You want to install it in a location where you can safely put the cord so it's not a trip hazard, and a place that's kind of out of sight, out of mind, so it's not obtrusive on the outside of your home. Yes? It's mostly important for the question was, the instructions say to install it on a north-facing side. That's ideal, that's not required. So a way you could get around that is if you look on this right-hand picture, you could mount that on the inside of the eave, and then you still have shade, and towards the bottom of the inside of the eave. So that'd be a way to still achieve the shade, but yet be on a sun-facing side of the home. So we'll jump into the installation side of things. There is a setup guide on the purpleair.com website. So we are providing a publicly available, commercially available product. So you have support from the Purple Air website and also support here from the project staff. So feel to reach out to us first, and then as well you can reach out to Purple Air or look on their website for resources. For Wi-Fi configuration, the first thing you want to do is power up this device. As I said before, you can do this close to your Wi-Fi router. You're going to be connecting the sensor to your Wi-Fi router. There's going to be a small red light on the inside of the sensor. You can see that, and that verifies that the power has been connected. If you don't see that red light, you have a faulty sensor or a faulty power supply. Once you do that, the sensor will start to broadcast its own Wi-Fi network, and that Wi-Fi network will be labeled Purple Air, and then a dash and 3 to 4 digits afterwards, and that will be the last 4 of the MAC address. This would be a good time as well to take a picture of the front of your sensor so that you get the MAC address. On the front of the sensor, there's the MAC address, and if you install it high up, you'll have to climb back up there to get that MAC address once you register it in that last step. So just kind of a heads up, take a picture of it so you have that information. Go on a Wi-Fi connected device. You can choose your cell phone or a laptop and connect to that Purple Air network. And once you click connect, then you're going to be able to either go to a web browser, or if you're on a laptop, it'll automatically open a web browser once you're connected to that Purple Air network. And when you go to that browser, you're going to go to a website 192.168.4.1, an internet browser. And you can see the settings here. It says internet may not be available. These 2 different pictures, those are both fine. Expect that. All these instructions as well are sent out to you when you receive your sensor. So at that section, you're going to click on the Wi-Fi settings. You can see that highlighted in blue, the blue circle. That will take you over to the next page. And there you're going to choose your home Wi-Fi. So you should have a home Wi-Fi network. That information, you'll find yours. It'll probably be the one that has the strongest signal. So you can see that this one here that's chosen has the strongest signal. So it also kind of shows you of what the signal is. So if you have your sensor in the location that you're installing it, you'll see what kind of a signal you have at that location. Go ahead and put your password in at the bottom and click save. And at that point, you successfully Wi-Fi configured your sensor. We'll stop there and look for any questions.
When I did mine, I found that it would only connect at the lower speed to the router.
The 2G?
Yeah.
Yes, that is correct. So the device will only connect to a 2G network. does not connect to 5G. Okay. Thank you for that. Yes. The question was, once you register the sensor, the network, the purple air monitor network disappears, and the question is, do we need to change the network to see it again? Yes. Good question. So the question is what if my Wi-Fi goes out, or I change networks, get a new service provider, and now I have a new SSID for my Wi-Fi and a new password? The Purple Air network will go back up. Once it does not connect to your home Wi-Fi, it'll start broadcasting its own Purple Air network again, and then you can reconfigure it at that time. Any other questions on the Wi-Fi configuration of the sensor? Yes, so this is screenshots of a phone. You can also do it on a laptop. So you connect to that network on a Wi-Fi enabled device, whether it's a phone or a laptop. So this is the connecting to the Wi-Fi. Once you connect to that Wi-Fi, then you go to an internet browser. You type in the 192.168.4.1, and that'll bring you here to the Wi-Fi settings. And so you're actually configuring that sensor through this settings page to your home Wi-Fi network. You're welcome. The last step is registration. So now that you're connected to your Wi-Fi, you need to register that device with the device manufacturer at purpleair.com/register. The first thing you're going to do is input your MAC ID address. That's that picture that you took of the front of your sensor. Put that 16 digits right there. The next part is the associated email. With that, you're going to need to put this email. That's the email that's associated with all of the sensors that are going out in this project. Next, you're going to click, you have the option of inside or outside. The sensor should be installed outside, and you should click outside here. Then you're going to put in your location name. The location name is given to you on the installation guide that's provided to you, and that's going to be AQMD_NASA_, and then a 3-digit number. So make sure that number is put in there. That way we can easily find those sensors, and as well on the Purple Air map, when we go there, we can search for those and see them all easily. For visibility, you're going to choose public so that everyone can see it on the interactive map. Then you're going to go down to the map. You're going to find your location. You can scroll through that map. It's interactive. You could skip the data providers, processors part. Just leave that with the default settings. And then you have the device owner's information. That's where you'll put in your personal information with your name, your email address, and a phone number. I believe the phone number is optional. I've registered probably about 100 of these, and I haven't received a single text message. Hit agree, hit register, and then your device will be successfully registered and should be sending data to the Purple Air map. Do we have any questions on the registration portion? Yes, the question was, if I registered my sensor and registered it under the wrong name, how can I fix that? The question is, and the answer is that you could just re-register the sensor under the correct name. So it'd be all the same settings and just put the correct name, and then that will reappear then on the Purple Air map with the correct device name. Yes. Thank you. The question was, is there an effort in this project to reach out to homeless that live next to roadways? We have not at this point. 2 of the requirements are power and Wi-Fi for the sensor. And so that's kind of limited our outreach. The suggestion is to work with public buildings. Thank you. Any other questions on the registration? All right. So once you register the sensor, you should be able to go to the real-time map. And we'll kind of just do a live demo of the real-time map. So this is a map. You can find this at purpleair.com/map. And you can see as I scroll in, the actual URL is changing. So you can copy that or even save that in one of your favorites once you get to a location that you like. And so you can scroll down into the South Coast region and you can click on a sensor. And if you click on a sensor, it'll pop up. It'll give you kind of its real-time reading. Right here. And then as well, it'll put in a time series of the last 3-4 days. If you want to compare your sensor to another sensor, you can go ahead and just click one in. So we'll go inland a little bit and we'll click another one. That'll then plot that sensor as well on that same time series plot on the left-hand side. And that's color-coded to the AQI that Pawan described earlier. And then if you want to click on even another sensor, it'll plot that as well. And you can see the scale dynamically changes as you click more sensors and you get to higher concentrations. Once you're inside this time series, you can also then unclick some if you want to get back to certain locations. And then it dynamically changes as well. So the layer that we're looking at right now with this map is currently the numbers are coded to AQI, Air Quality Index. That can be changed here on the map data layer. So you go here, you can change that to AQI based on PM10. You can also change it for temperature. So if you want to look at temperature, we can click on that. And you can see how it's cooler towards the coast. It gets hotter as you go out more towards the desert regions. Look at humidity as well. You'll see a similar trend. It's more humid towards the coast, dries out. And if you zoom out, you can really see that as you get out towards the Palm Springs region. And then if you would like to look at concentration values, those would be here, raw PM 1.0, 2.5, and 10. So you can click on those, that'll change, and then the numbers will be corresponding to the actual mass concentration values. And then there's a search feature up here in the top. So if you type in your sensor, you should be able to type that in, and then you can click your sensor and it'll automatically take you right there. Then you can click on it, get your data for current, 10 minutes, and all those averages if you're looking for over time and your time series as well. Yeah, so the question is, how do we save our station as a favorite? There's not a, the URL doesn't actually change. The way you can do it is the top address bar changes dynamically based on your lat long and view. And so if you find where your sensor is, you can save that address right there. And if you would put that in a new browser, it would pop you in right there to that same location. And then you could bookmark that URL once you're right above your sensor. But it would still take one click to get to yours and see that data. Yes. Yes, so if you log in to here, so if you create an account, you can log in there. It needs to be, I believe, a Gmail account. So you have a Gmail account, you can create an account. So you can associate that when you do your device and you register it to the email address that you would like, then you create an account here with that same email address. And then if you click that, just show my device, all the other devices will go away and it'll just show yours. Any other questions? Yes.
I don't know if it's appropriate for this point in the workshop, but it was mentioned earlier that the AQMD
Yeah, so what we're viewing here, if you click on a sensor, so this would be an AQMD NASA 2 sensor. Right now, let's change the map layer to AQI, PM2.5 AQI. So we're on that. And so what it's showing here is AQI values with different time averages. So the typical standard way that AQI is calculated, if you look at US EPA guidelines on it, is either in the past has been a 24-hour calculation, and then they have adjusted that to a nowcast method, which is actually a rolling 1-hour average, which heavily weights their most recent hours. Here, they're just taking the concentration values and then corresponding that to AQIs, very similar to the chart that was shown by Pawan. But you can do that at different time averages. So you can see how now it's 55. The 10-minute average for AQI is 55. You see how that changes as you go towards 6 hours, 1 day, 1 week. Yes, I will touch on that in just a minute, and then Ashley will go through that in detail. So the last thing I guess I can show you is if you want to share information, you can click this button here. You can print chart, download a PDF or different image formats. With that as well, the download feature is there. So if you want to look at your historical data, you can find that here. The website is purpleair.com/sensor list. Once you go there, you're going to want to hit Control F and then search for the name of your sensor. Just type in NASA, it'll give you a list of all of them. And then you can click on the various sensors, and Ashley will highlight that. With that, I'm going to conclude, and we're going to have a short break. So if you want to come try and register a sensor, get it on your phone and kind of connect to it, we can do that in a short break. And then Ashley's going to follow up with going into detail on data downloads and some tools for analyzing data if you want to download it and analyze it in Excel. Yeah, we'll do a 10-minute break. Yeah, go ahead and send an email to Olga, and you can copy myself. Like from a home, or like from at the same location, or to a completely? Okay, yeah, that's fine. I wouldn't worry about it. Yeah.
Shall we start? Okay, hi everyone again. My name is Vasilios Papapostolou and I'm the program supervisor of the Air Quality Sensor Performance Evaluation Center, or AQSpec. I'm just going to take 3 minutes of your time. I would like to just point out about, a little bit about the program here that we have, and a project that all of these tools that Ashley is going to talk to you about have derived from. So low-cost sensors, resources, and tools for data analysis. This is going to be our next session. And a little bit of an overview about the AQSpec program, background on the program and the EPA-funded STAR grant, what we can do with the data. Ashley's going to talk about it. She's used about 2 years worth of data and conducted a preliminary analysis. You're going to see some results today, and then ways you can engage with the data and the resources as part of this NASA project. So we're here to support the work by the 2 co-PIs, Pawan with NASA and Olga in this NASA Citizen Science Project. And we're supporting by providing these tools that Ashley is going to talk about. A little bit about AQSpec. It's a program that was established about 5 years ago, evaluating low-cost commercially available sensors for their performance, borrowing, buying, or being donated those devices by the vendors, the manufacturers, the developers, and conducting an evaluation where we explore their performance. And as we identify good sensors, good performing devices, we assign those to different projects, or projects that are internal here or external with other collaborators. One of those is this NASA project. So how do we bring the sensors in for testing? You see some of the criteria there. Commercially available measuring criteria, pollutants, real-time or near real-time measurements, continuous operation, and retrievable data that we have access to, especially during the evaluation process. Now, sensor evaluation work and any sensor-related projects that are linked to AQSpec. One of them is the EPA-funded STAR grant. We are one of the 6 recipients. The program started back in 2016. And the title of the project, to give you an idea, is Engage, Educate, and Empower California Communities on the Use and Application of Low-Cost Air Monitoring Sensors. The program has been running for 3 years already, plus. And in this project, we're also working with communities and community members to understand the technology, the sensor technology, understand how people react to this type of new technology, understand the data, interpret the data, work with the data, and so on and so forth. We've distributed about 400 PM sensors, very much the same sensor as you're using here in this project. We're working with 14 communities in the state of California, from down here all the way up to the north, Richmond and Oakland. And it's an ongoing process. Out of this project, the outcome of this project will be an educational toolkit that will consist of different types of materials, including tools like the data analysis tools to handle, process, analyze, and handle this data from the purple air sensor. So this is here a map to give you an idea how our sensors under that STAR grant project look like on a map, and the distribution of them in the state of California. And I'll stop here and pass it to Ashley. She's an AQ specialist in AQSpec that she joined us last October, about a year now. She's with us. And she has been working on developing those data analysis tools very much needed in the communities by the community members to go in and work with the data from their sensors. So, Ashley?
Thank you so much, Vasilios. And I will move on. So as was previously mentioned, I'm going to begin with a little bit of a preliminary analysis from the sensors in of the data from the sensors in this network to sort of illustrate the types of questions we can ask and the types of analyses we can conduct with this type of low-cost sensor data. I'll be showing you data from 46 of the sensors in this network. And yes, nearly 2 years of data from roughly September of 2017 to August of 2019. So first off, where are the sensors? So this is a quick snapshot of most of the network sensors that were active as of last week. You can see there's a pretty wide spread with a pretty high concentration in central LA. And how much data does that add up to? So this chart shows us when we have data from which sensor. So there's 46 sensors, and where we have solid black lines means we have data. So if you look at the one on the very bottom, you'll notice we have nearly 2 years of complete data. And these sensors are recording data points every 2 minutes. So that adds up to quite a lot of data. And it illustrates the need and the value of having data analysis tools to more easily pull out information. You wouldn't want to be looking at the raw data for all of these sensors. So here's another way we can visualize the data. This is a complete time series of all the available data from all the sensors, all 46. Each dot represents an hourly average. And here we can begin to see some interesting patterns emerge. We see when the sensors are in agreement with each other, when there's more spread and differences between the sensors. And we can also see interesting events start to emerge. Let's see. I don't know if the dot doesn't appear to show up. So do you guys see those peaks happening? There's 2 of them. Let me go back here so I can point at it. So guesses on what these events might be? 4th of July, fireworks, exactly. So 2 years, both in 2018 and 2019, we can see the emissions from the 4th of July fireworks, in addition to other events. So here we're showing a calendar plot. So this is a plot that our team has found is really intuitive, particularly for community-based and citizen scientists to understand. So it's illustrating the daily average laid out across the calendar. That warmer purple color is higher PM 2.5 levels, and the light blue is lower levels. And here I'm showing all of the data available from one sensor, AQMD NASA 18. I selected that sensor because it was pretty central to the network and it had quite a lot of complete data. This is a great way to get an overview of the data and start to zoom into air quality events that you might want to learn more about. So going back to the 4th of July, we see that event pop up for this sensor as well. But not only can we take these big zoomed out views with these sensor networks, the value is having the spatial variability available to us and the high time resolution data. So here we're showing the average PM 2.5 values for each sensor that was active on the 4th and 5th of July that just passed in 2019. And again, the light blue is lower PM 2.5 levels and the purple is higher. And we start to see this gradient. Outside of the city and on the coast, we see lower levels and higher levels as we move inland, probably driven by where the fireworks were occurring and how the emissions were being transported. And that yellow circle is indicating where that sensor 18 is. And the time series on the right takes advantage of the high time resolution data that we have from the sensors. So this is the raw 2-minute data. And we can see in the evening of the 4th, the levels peak. The emissions hang out overnight, and then they disperse the next day, and levels go back down to what they were before the event. So going back to the calendar plot, another, of course, important event are wildfires. So you all probably remember that weekend back in this past November during the Woolsey fire, when the wind suddenly changed direction and we had a lot of emissions in the central part of the city. So we can see that weekend here, November 10th and 11th of 2018. And we can also take a deeper look at that data, again, leveraging the high time resolution nature of the data. So here in this time series, we see lower levels. And when we add in supplemental data, we can get more context and better understand what's going on. So here I'm adding in wind speed and wind direction. So this is a wind rose showing us where the wind is coming from primarily for the day shown in the yellow box. So we see before the emissions moved in, we've got winds primarily out of the southeast and the west. Then we get a lot more winds from northerly directions, and that's when we start to see the emissions rise in the city. The next day, we're still getting some winds out of the north, more out of the west. And then one more day later, most of the winds are primarily coming out of the southwest, and we see the levels clear out. And again, this is the 2-minute raw data from all of the purple air sensors. So these sensors are great for helping us dig into these trends across space and time. And in addition to that, Brandon showed you guys the purple air map. We can also get real-time data from the sensors and see these events in real time. We can compare our neighborhoods to other neighborhoods, our sensor to our neighbor's sensor, and really start to get a sense of what's going on at the local level. So that's a brief overview of some of the data. So now I'm going to talk about different ways you guys can engage with the data. So all of that analysis was done in R. It's a statistical analysis software. Who knows what R is? Who's familiar? I got some hands? Okay, cool. So if anyone wants to talk more about different ways to look at sensor data in R, I'd be happy to. And I'm also going to talk about more accessible ways that are better for community scientists who really want to get in there and work with the data. So as Brandon mentioned, we can download the raw sensor data. Excel is also a great tool for working with the data. And then the EPA has developed a web-based data visualization tool called Redigo that I'm going to show you guys. And what our team, the AQ Spec Group, has done is we've put together a number of resources to make working with the data in Excel and with Redigo a little bit easier. So Brandon briefly showed this page. So this is the sensor download site. So this is where you want to go if you want to get access to all of that historic and all of that raw high time resolution data. So it's pretty straightforward to use. You choose your sensors. If you've got a PC, you can Control F and you get a box where you can enter in your precise sensor's name so that you don't have to scroll through the entire list of every purple air sensor. And you'll also notice that there's 2 of every sensor. That is the data from the 2 duplicate raw sensors that Brandon mentioned inside of the purple air. So they're essentially referred to as channel A and channel B. So channel A is that primary sensor that shows up on the purple air map, and then channel B is the data from that second sensor. Next, you'll enter in your start date and end date of the data you'd like to look at, and then you just hit download, and it all comes to your computer as Excel files that are easy to open and pretty much ready to go. So let's talk about what the data looks like. So when you download your data from a single sensor, if you choose the channel A and channel B, you'll notice you get 4 data files. So you'll probably want to be working with the primary files. The secondary data files, you can think of those as the more raw data it's what purple air is converting into the more usable mass concentrations. So if you want that final finished process data, you're going to want to go to those primary data files. And here's what one of those looks like. And you don't have to remember all of this. We have PDFs of all the steps that you can go through to access the data and make it easier to work with that we can share with you guys. So this is just to give you an idea of the options that are out there for working with this data. So one quick thing to note, the timestamp for all purple air sensors when you download it is in UTC, not Pacific Standard Time, not your local time. So you'll want to think about whether you want to work with that in the central coordinated UTC GMT time or if you want to convert it to local time. And then the data that you're going to want to use for your analysis is going to be the PM1, PM2.5, and PM10 data that is in column C, D, and E. You'll notice after it, there's an underscore, CF, underscore, ATM, underscore, micrograms per meter cubed. That's showing you that it's the manufacturer has applied a correction factor to correct for environmental cross sensitivities, and it's also the units, the micrograms per meter cubed. One of the tools developed by our staff is a macro. So those of you who are comfortable with Excel, how many people are familiar with macros? Great, awesome. So I don't need to give too much background. So it's a simple program to take that UTC timestamp and convert it into local time. So we have that tool that we can share as well. You just open our tool containing the macro, you open your purple air file, hit Control T, and it gives you that new column with your local time. And you're ready to go. And Excel is a great tool if you want to have a lot of control over what you're doing. You can make really specific plots, you can calculate statistics, averages, minimums, maximums, etc. And there's tons of online tools to learn more about Excel. So the other tool I'd like to talk about, backing up a little bit, the easiest, quickest way to work with your or to interact with your purple air sensor data is going to be that map, that online purple air map. I would say Excel is probably going to be a little bit more difficult. And sort of the middle ground is this tool Redigo. So this is a free, open, web-based tool built by EPA. And basically, if you take your purple air data, we have a few short steps to get it ready for Redigo. And then you can upload it into Redigo, you can make maps, you can make time series, and you can add in data from AirNow reference sites. Again, you don't need to remember these steps. I'm just going to quickly give you an illustration of what you need to do to get your data into Redigo. And then I'll do a quick demo. So basically, we have a CSV template for Redigo available for anyone who would like to use it. It's pretty simple. What's important is that the column headers are named very precisely and that they're named what the Redigo tool is expecting so that your data uploads properly. Basically, you just need to copy and paste in your PM concentration data. You can add temperature and humidity if you also want to look at that. And then you need to convert your timestamp. So Redigo has an online timestamp converter that I'll show you. You just copy and paste the data from the raw Purple Air file, select the right format, hit convert, and grab your converted timestamp and paste that back into your new file. And the last thing you have to do is add in the ID for your sensor and the latitude and longitude. And a quick cheat, you can grab the latitude and longitude from the file name that you've downloaded. So you copy and paste those in and use the autofill feature to just drag the data all the way down. So, all right, so let's go to, this is where you can find Redigo, and this is what it looks like. It's the home page. They've got some really wonderful tutorials. So the resources developed by our team are intended to help you get the data from the raw format that Purple Air gives you into the tool. And then once you're here, you should take a look at their tutorials and FAQs. Really quickly, I'll show you the timestamp converter, because that's one important thing you'll need. It's really simple. You just grab this format here with the time zone at the end. That's going to recognize that UTC that it automatically comes offline with. Put the Purple Air time series here and get your converted time series here. So I went ahead and loaded a CSV file that contained data from 13 of the NASA AQMD sensors. It's the first week of July, again, from this past year, 2019. So you can see right away, all of your sites get plotted on the map. You can see the blue dots here. There's this time slider at the top that you can use to explore individual points in time and see what concentrations were, at what place, at what time. And then you can add other plots. So got the time series plot. So again, this is really similar to the plot that I made in R. It's got data from all 13 sensors plotted together on a time series. And that can be explored using that time slider as well. Beyond that, we can also add things like PM10 data. So we can look at PM2.5 and PM10. We see there were increases in PM2.5 and 10 on July 4th. And I forgot to do this, it's still in GMT. Might make a little bit more sense there. So now it's happening on the evening of July 4th. Another thing we can do is take a look at sites on the time series individually. So we're limited to 5 at a time, but we can grab any 5 and compare where they are on the map and what they were doing in time. So, and the last feature I would like to show you, that I think is really powerful, is how we can add in other data, meteorological data and data from reference sites, AirNow reference sites. So we can add all the reference sites to the map so you can see where the sensors are in relation to regulatory monitoring sites. We can select them. And then we can add that data and compare. So we see that it looks like the sensors, or at least some of the sensors, we're seeing a little bit higher levels than that central LA site. They are located in very different places, so that could be why. So we can also dig in and sort of see what's going on. Let's grab the site closest. When we grab the Purple Air closest to that monitoring site, we see the levels are pretty comparable. And then when we grab one further away, we see higher PM2.5 levels. And we can also switch over to this site. Let's see. So, and we see that we did in fact see higher levels at that reference site as well for PM2.5. And this site also allows you to add reference temperature data, pressure data, and wind speed data as well. And there are a few other analysis features. I would encourage you, if you're interested in using this tool, to check out the tutorials. So to sum up, there's a list of resources here. So all of the data is available for downloading at that website, the Purple Air Sensor List site. We also have our macro tool that can help you get the timestamp into a more usable local timestamp. And then we have instructions to get your data into Redigo, step-by-step instructions. And we also have a data analysis guide to help you think of and shape your questions as you consider how to explore your local air quality and what you're learning through your sensor. And I have my contact info here. If any of you community scientists would like help with using any of these tools or troubleshooting, please don't hesitate to reach out. So, any questions? That might actually be a good question for Olga.
And that sensor is about PM. So we developed these tools. These tools are freshly developed actually right now to accommodate analysis of data from that device under the Stargram project, and now supporting the NASA project that is using the same sensor. Moving forward, we will be adding more projects using sensors that also measure other criteria pollutants beyond PM.5 and PM10, ozone, NO2, CO. And if there is a need for us or community members or other scientists to use tools to analyze that data from those sensors, we might be developing those as well. So that's where we're at. We've started with handling PM data using these tools. If there is any interest, we might as well, you know.
Yeah, so the comment was that the ozone is also like a very important pollutant. So for this particular project, the reason we concentrated on PM 2.5, at the time when we were developing a proposal, we essentially looked, what are the available local sensors that also produce reliable data, and also what are the NASA, satellite data products, and what questions we can answer combining those two. And at that time, PM sensors were the ones who were showing the most promise, and there were also sensors on the market already that we could use. But definitely, as as the sensor technology progresses, that other project may come online, to look at more pollutants. Yeah. Yep. So this particular sensor is capable of measuring PM10, PM2.5, and PM1. So, so you get this information essentially for free with every sensor. This project specifically, we're mostly going to be focusing actually on PM2.5. Yeah, definitely. Yeah, yeah. So if you look at specifically Purple Air map, right, there are centers sort of around the world that have like high concentrations of these purple air devices, because like we're distributing some here, but there are some people who purchasing them on their own and installing them. So there's definitely an opportunity to use this data on local scale or global scale, to make some conclusions. Yeah. That's an excellent question. Ashley probably would be the best to answer that. Yeah.
Sorry, your question was, I was pulling the map up. Your question was, where should you start with the averaging? Or the amount of data. Perfect. Sure. Yeah, I would definitely. I would recommend starting with a small bite. I would say anywhere between 1 day and a week would be great to start. That way, you have enough data that you can sort of do a sanity check and see, am I seeing the trends I would expect? So for example, you can take a look at the temperature signal going up during the day, going down at night, and you can start to get a handle of what the data looks like and interacting with it. But those files are going to be small enough that they're going to be really quick and easy to run in Excel. When you start getting into a year's worth of data, Excel gets really bogged down and it can be a little bit difficult. So yeah, I'd say a day to a week is a good starting range. Okay.
So you mean like not necessarily moving the sensor around, but like see what changes? Yeah. Um, well, no, I would say I would encourage that, right? Because at the end of the day, like, this sensor allows you to look at your like really micro, level air quality. So if you can actually, do make some changes that will change your PM concentration in your little bubble, then that would be interesting. I've never had this question before. Yeah, yeah, yeah. Oh, again, Pavan is.
Just because when we are like we were saying, when we start analyzing the data from large number of sensors, then at least we know, okay, this is specific case for this reason. That's why you see abnormal values. So just for our information, but feel free to do it.
Yeah. Yeah, we like, we're air quality agency, so no, like it's not going to be on our radar, and specifically not for that project for sure. Yeah. Great. Okay. Thank you. Okay. Thank you. Any other questions?
That website is all raw data. So it's going to be that 2 minute, yeah, as the sensor is updating, it's that high time resolution data. I don't believe they have an option for hourly data. Yes, on the Purple Air sensor down list site. Mhm. You cannot edit any of the data in the Purple Air sensor database, but that brings up a great point, and this is something we've done on other projects. It's always great to keep those sort of log notes of events. Like if you see an air quality event and you have an obvious cause, that's great information, that context to have when people are going back and analyzing the data. So if you keep sort of notes, that would be incredible. So thank you. No, we love the stories. Please share.
Okay. So, so what we are going to do is now I will give you a very brief overview of what we can see from the satellite in terms of particulate air pollution. I'll give you some examples, show them how to interpret that data in imageries. And then in the last, we will, if those who have either phone or laptop, will show you a tool where you can access real-time satellite data. And it's really easy and free to use. So I'll show you that in the last with some example. So there are many different types of satellites. They can be anywhere from 300 kilometer above the Earth to millions of miles away. And all of these different types of satellite provide different piece of information about Earth atmosphere system. And we are specifically in this project interested about the air pollution, in particular particulate matter or PM 2.5. So this is just an example from a satellite called Discover Deep Space Climate Observatory, which was launched in a orbit called L1 orbit, which is about 1.5 million kilometer above the Earth. So it's really, really far away. It can see moon and Earth together. So you see on the left side, there's a moon, actually an Earth, and this photograph is taken by this Discover satellite. And this is operational right now. So it provides image every 90 minutes, one image of the Earth, and it makes measurement in several spectral channels. So you have a quantitative, just not pretty picture, but quantitative numbers from the satellite. And if you zoom in this satellite data, they are about 20 kilometer in spatial resolution, then you can see some of those air pollution events happens on the Earth. So on the right is just an example from 2017, I believe. This is fires in California, and you can see actually the smoke plumes coming out from the fires. So this is a really incredible observation from that high altitude, which we are getting from this kind of satellite. So just give you, again, all the imageries available from this website. You can actually see that every 90 minutes, freely available for anyone to use and download it. Okay, so why we need satellite data, right? Why means we have been monitoring air quality from these ground measurements from last 20, 30, 40 years. So why we are using, why we need satellite data? So what you see here is all these dots are showing the locations of the ground monitors where government agencies like AQMD or EPA makes measurements, and not only in the US, but all around the world for regulatory purposes, okay? These are not Purple Air Network. This are regulatory reference method monitors operated by government agencies, pollution control boards all around the world. And if you look this picture, then you will see huge data gaps all around the world, right? Means African continent, there's hardly any monitoring station there. Even in the South America, large part of Asia is also very data spare region, right? So the idea is, can we use satellite data to fill some of these gaps all around the world so that we can actually look a global view of air pollutions from the satellite. So these ground measurements are really great. Means the idea is not to replace these ground measurements. We will always need ground measurement to validate the satellite data, to cross-check, to do better job in satellite data. So, but the idea is to fill some of the gap, use the satellite data where we cannot monitor the air quality for many different reasons, okay? So what do we get from the satellite data? So this is, I'm just showing you an example. This is a RGB or true color image, which is created using measurement from the satellite in 3 different band: red, green, and red, blue, and green. So it's RGB. When you make measurement in those 3 spectral channels, you get those 3 different measurement. And when you try to combine them in a computer algorithm display, then you get this nice looking RGB or true color image. We call it true color because that's what our human eye sees. So if you go out, like clouds will look white, vegetation will look a little greenish or dark, and that's what the satellite image is showing you. So this is again the fire case in October 2016, I believe, and this is from one of the satellite. Its name is VIRS. It's a joint NOAA-NASA project, and this specific satellite make measurement twice in a day, one in daytime during afternoon about 1:30 local solar time, and one in the nighttime. So this is from the daytime image because those red, green, and blue lights is only available during daytime. We don't have those in the nighttime. In nighttime, it make measurement in other spectral channels. So on October 8, you can see on that circle, looks very clean. There was no smoke or anything. On October 9, I think the fire started sometime late in October 8, probably. And you can see those huge smoke plumes coming out of those fires and actually going over the oceans. So that's the first visual capture from the satellite about those fires, which we can see immediately. And all this data is available like in real time, almost within few hours of satellite overpass. So during nighttime, the same satellite has another band called day-night band. It basically designed to make measurement of the city lights where human activity is happening. So there is any lights which is out there going in the space, the satellite is making measurement. So there is a specific band for that. And it's not only lights capturing from the city light, but any source. So when there is fire happens, there are huge amount of lights emerge from those fires. So again, if you look that circle on October 8th, that area where there were fires, you don't see actually large light. On October 9, you can see that lights coming out of those fires. So this is another way for us to actually detect the fire locations during the nighttime. So based on these measurements and few other spectral channels, there are computer algorithms which can actually detect individual fires locations. And this specific satellite has a spatial resolution of 375 meter. So any fire which is smaller than that or larger than, or if it is very intense, if we have enough thermal signal from that fires, the satellite will detect it. And once it is detected, we will know exact location in terms of the latitude and longitude. And those red dots are actually showing those fire locations. So there are multiple fires happening in those locations. Again, you don't see those red dots on October 8, but you see them on October 9. So if you combine all these three, you will see they are exactly pointing where the smokes are coming out. So these are just detection of those fires are looking, right? If you want to quantify that in terms of pollution, right, we need to have some quantitative values. So when you combine all this data, again, you apply some physics and some computer algorithms, and you calculate something called aerosol optical depth. This is a quantity which we calculate to define or to quantify how much particles, how many particles of aerosols or small size particles are there in the entire column of the atmosphere. So when I say entire column, means from the surface where we breathe to the top of the atmosphere or to the height of the satellite. So that represent, but often, most of the particles are actually located within 1 to 2 kilometer of atmospheric layers. So you can assume that often whatever this aerosol optical depth is representing within 1 or 2 kilometer of the air. So again, you can see the blue color shows smaller values. Aerosol optical depth is a unitless quantity. It does not have any unit. It can typically, for clean conditions, it's about 0.1, 0.2. But if it is polluted condition, those red values are larger than 1 or 2. So during those smoke plume, you can see that red values, all those values are really, really high and showing very high concentration of smoke. Now, this AOD showing high value does not mean that at the surface also PM2.5 will be high. Okay, this is entire column again. So that is why we need some kind of another set of tools or algorithms to convert that aerosol optical depth into nose level air pollution or particulate matter. And these specific sensors or any other reference method sensor help us to actually develop those algorithms. So we did that again during the same fires. No, this is different fire this is in Bay Area. And what this is showing here is on the left is satellite aerosol optical depth, which is scaled on the top. You can see the color coding. And on the right is this measurement from measurement of PM2.5 from these purple air sensors in the Bay Area. And the circle over there is changing the date. This is October, started October 8. This is the same fire which I was showing the picture earlier. It started around October 8 or 9, and then it goes until October 16, 17, I believe. So what you can see here is, one thing is both satellite measurement and surface measurement are responding in a very similar way to the change in concentration of particles in the air because of the fires. So this gives us a good signal that whatever this PM2.5 is measured by these sensors, satellite is giving you a similar information. It's a different quantity, okay? But the information is very similar. I mean, we can use, there's a relationship between these two quantity, which we can use further to actually get from get PM 2.5 from the satellite measurement. So this is a just an experiment which we did, and it shows very, it gives a lot of confidence in terms of how we can use the satellite data. Okay, so what I'm going to do is now just give you a brief overview of how the satellite actually works and what different satellites are there, and then finally we'll look some of the data sets ourselves. So most of the satellites are remote sensing sensors, means they are not sampling air directly, but they are indirect measurement. So they either they can be, or what you can call them, an optical sensors. So, and they works in a different range of spectra of solar spectrum radiation. Some of them are works in UV radiation, some of them in visible, some of them in IR, near IR, microwaves. So different range of sensor, depending on your application, you get information. So the remote sensing is like, this is a typical definition when you try to collect the information from a distance about object. That's what remote sensing is. So our eyes, your cameras, and all those things are really good example of remote sensing sensors. The purple air sensor, which is there, is in a way is also a remote sensing sensor. It's an optical base. Satellites are also remote sensing sensor. Okay, so now these sensors can be put out on a different platforms and a different height. Again, it depends on what information you want to get and how much details you want to get. They can be located on the ground, on aircraft, balloons, small satellites or cube satellites. And then the International Space Station, everybody heard there are a lot of actually Earth observing satellite sensors mounted on that nowadays. Which is about 300 to 400 kilometer up. And then you have other satellite, which I was showing the picture, which are about 800 kilometers. And then as you go up at 36,000 kilometer, that's the orbit where most of the weather satellites are located, like GOES satellite, which provides you weather information. It's called a geostationary orbit. And then there are other orbits like L1 orbit and other orbits for different applications. So higher as you go in the terms of the orbit, those sensors are often used for space weather monitoring. For Earth monitoring, most of the sensors are below 36,000 kilometer. So how does satellite works? You have a source of energy, which is sun. It emits electromagnetic spectrum in all the wavelengths. That radiation come down to the Earth. It interacts with the component in the atmospheres, which are clouds, particles, gases, air molecules, water vapor. Anything which is in the atmosphere will interact with this incoming solar radiation. And depending on their property, depending on the properties, shape, type, size of those particles, that will have a different type of interaction from the incoming radiation, and either it will reflect back to the space, it will absorb, or it will transmit to the ground. Those which is transmitting to the ground again will interact with the objects which are on the ground, either tree, water, land, anything. And again, everything will, the reflected part will go back to this space, and that's where your satellite is located. And satellite is making that reflected light, measurement of that reflected light. So remember, satellites are far away. They are not sampling your air directly like these sensors. They are making indirect measurement of effect on the light, how the light is interacting with those particles. Once you get those radiance measurement from the satellite, then they send out to the Earth, and then that's where our job starts. Then we actually analyze that data, try to separate different component from this signal, and quantify how many particles are there in the air using some of the algorithms. So this is just an example showing how a polar orbiting satellites makes measurement. I'm just going to move it forward so that you can see the daytime. So satellite, this is a specific orbit. It's called polar orbiting. And polar orbiting means the satellite is actually rotating pole to pole in circular orbits, and Earth underneath is rotating, right? So whichever part of the Earth is coming in the path of satellite, it will make measurement of that. And that's how you are seeing this. So this block of measurement is called orbit, one orbit. So from South Pole to North Pole, it's one orbit. And this specific satellite, it's called MODIS. There are two MODIS sensors in two different satellites. One is in the morning on a Terra satellite, and one in the afternoon in the Aqua satellite. So they are about making measurement 3 hours apart from each other. So in a one day, it covers the entire globe. Actually, there are 15 to 16 orbit on a given day, and it does cover the entire globe. But there are some gaps in between. You can see those black lines. Those are orbital gaps. That depends, again, different satellite will have a different width of that orbit. So depending on how the swath width is, some satellite will cover the entire globe, some will have the gaps. So this is specific has some very small gaps in the only equator region. If you see, those gaps are actually only equator region plus minus 30 degree. Other than that, in the polar regions, you will see actually multiple orbit on a given day. So you have more than one observation per day in high latitude. So this is how the polar orbiting works. Now, the weather satellite, which I was talking about, the geostationary satellite, which is about 36,000 kilometer in the height. And these are specifically in the US, managed by NOAA. Means it's a partnership between NOAA and NASA. NASA managed the satellite, but the NOAA managed the data and everything else. They are primary users of the data. It is specifically designed for weather monitoring, but there are many other applications. So they have become also very advanced in recent time. This is image from one of the recently launched satellite like 2 years ago. It's called GOES-R or GOES East, now it is called. And this is in geostationary orbit. So the geostationary orbit means, as name suggests, this satellite sees the relative motion between the satellite and Earth is fixed. So they will always see each other as at the same place. So the satellite will look same portion of the Earth all the time. So the limitation of this satellite, this orbit or this satellite is it won't have a global coverage. It will have only regional coverage. So this specific satellite is looking entire Western Hemisphere, specifically both Americas, Pacific Ocean and Atlantic Ocean, and some portion of Northern Africa. But the good thing about this satellite is it can make frequent measurement. The polar orbiting, the earlier I was showing, was only making one measurement in a daytime. But this, since it is fixed in orbit, it makes very frequent measurement. So this specific satellite provides this type of image every 10 minutes. And it has a 16 different spectral channels. So you get, the resolution is about 1 kilometer of the satellite. So every 1 kilometer space on the Earth's surface, you have one measurement in 16 different spectral channel. And that is really helpful because that way you can extract a lot of information about the Earth, atmosphere, and water bodies. So does anybody notice a black thing moving around? What is that? Sorry? Solar eclipse, yes. So this is during the last solar eclipse which happened last year, right? Was it last year or 17, I think. Anyway, that solar eclipse actually, the shadow is moving from west coast to the east coast, so you can see actually from the satellite. So this, because of the resolution and because of the advance of the satellite, you can see actually very small things in this. Sometime if there is a rocket launch, you can see actually in this. There are many examples. I'll show you a website where you can track all those events actually. It can also see International Space Station as it is moving. So this is amazing. It's very high resolution, very capable of. Okay, let me skip this little bit and go. So how do we get to the particles, right? We are trying to get the concentration of these particles in the atmosphere from the satellite data. So how do we know from those images? So since we are making measurement in various spectral channel, different wavelengths of solar light, uh, depending on the particles properties, depending on their shape, their optical property, how they will behave with when they interact with a specific solar spectrum light, they will actually provide different visuals in satellite imagery. So these are all RGBs showing different types of particles in the atmosphere. And what you can see is just looking these 4 images, you can see they are either different color, or they are providing different textures, or they are distributed differently in the image. So on the bottom right, can anybody tells me what could be that be? What kind of particles will produce that kind of image? Yes. Yes, so that's right. That's oil fire in India. There was a big fires in an oil depot, and Modis happens to overpass during that time, and it captures that image. So because of the high concentration of black carbon, it produces you that kind of image. On the top right is what is on the top right? Volcano. So that's a volcanic eruption, and you can see almost like a cloud, right? Because this specific volcano was producing a lot of SO2, the sulfate, and sulfate is very scattering in nature. I mean, they reflect a lot of light, uh, opposite to what black carbon will do. So they produce a spectrally smooth radiation, means all the channel which have similar reflectance, and that's why they look whitish in color. On the top left, that's what is that? Dust, right? So that's dust in Australia, and you can see that in a brownish color. So means if you look carefully, they are very similar to what you will see from your human eye, right? So if you look, so those brownish color is a dust storm, and these dust particles are usually large in size. So if you are making PM2.5 measurement, uh, often dust are larger than PM2.5. They are falls in PM10 category most, but there is also fine dust which actually contribute to PM2.5. And on the bottom left is a mixture of haze and smoke over Bangladesh and India, which showing in a very different, very smooth features, but hazy, right? So these are all. This is another example. Similarly, on the top left is dust coming out of Saharan deserts in Africa. So you can see the contrast. Over land, you won't see difference between the land underneath and the dust in the atmosphere. But as soon as it goes over the ocean, because of the dark surface, you can see that dust concentration or the contrast over ocean. Similarly, fires, smoke, again, this is a California example from the 2007, and those 2 bottom examples are basically pollution coming out of the East Coast over ocean. So all this different texture, different spatial orientation of these aerosol particles and their shape and size help us actually to determine what kind of particles are there and to quantify them in accurately in our algorithms. So this is again an example from fires in California. Again, this is from the GHOST satellite, which I was showing every 5 minutes over continental United States. And you can see that how the smoke is actually coming out of those fires and moving towards the ocean. And since this is very high frequency measurement, we can use this measurement to actually alert public where the smoke is transporting, right? And then you can actually do a little bit more computing and calculate the air quality because of those smoke plumes. Okay, so another example, again from the GOES-R satellite. This is fires. This is August 2017. There were a lot of fires in the state of Washington, Oregon, and Canada. So you can see on the top right, the smoke plumes actually is moving all over the US. And when we convert that, that quantity into aerosol optical depth, you can see that red colors over the US. That's basically smoke plumes from those fires. Again, every 15 minute, this is every 15-minute data. At the same time, you can see there were a lot of fires going on in Amazonia, Amazon forest in Brazil. And you can see again that red colors in the aerosol optical depth over that region, which is showing the high concentration of smoke. You can see other weather features. There was a hurricane going on at that time, multiple hurricane actually. So all those weather pattern sometimes helps transport these smoke or dust to the long distance. And I'll show you some example for that in a minute. Can anybody tell me why there is a big white hole in the middle of the right image? Sorry? Moon? Okay, anyone else? Sorry? Yeah, that's right. So if you look the left image carefully, you will see there is a glow which is moving from the east to west in that image, and that's basically sun's reflection over water. So you will only see over water. You won't see that over land. So that specific area, since because of its high reflectivity, the way the sun and satellites are located at that particular locations, it's called glint region. And those glint region, we cannot actually get the particle information very accurately, so we don't use that data. And that is why you see a big hole in our data on the right side image. So satellite is still making measurement, but our algorithm cannot retrieve the particle information in that region. And that's why you see that big hole on the right side. Okay, so this is just over US, right? So our goal is to get this globally. So what we do is, there are so many different satellites, not only over US, but other parts of the world. And they are in different orbits, means either they're in geostationary orbit or polar orbit. So either they are giving you one observation in a day or multiple observation in a day. So what we are trying to do is we are trying to combine all this data into a single data sets and trying to get every 30-minute, every 1 hour pictures of entire globe as much as possible. So what we did here on the left, you see individual satellites, the small globes. So you have a goes east, goes west. These are two US NOAA satellites looking east coast and west coast. You have Himawari, which is a Japanese satellite looking Asia. At the same time, it's almost identical to GOES-R satellite. And then you have multiple polar orbiting satellite, MODIS Aqua, MODIS Terra, VIRS. And then when you combine all together, the middle globe is the picture you get. So you will see that there's a lot more data over US and America, over Asia, and there's a huge gap over Africa, even in the satellite data. The reason is we do not have a good similar quality satellite over Europe and Africa right now. It will happen in next 2 years. There are plans to launch some similar satellite over that location. Once we have that, we will have a very good global coverage every 10-15 minutes. Okay, with that, so this is the final slide. Once you have all this data, means the satellite is going to tell you, or this purple air sensors or reference method are going to tell you what is happening now, right? Or what happened in the past. But in order to plan your days, in order to do things activity in advance, you need to know what is going to happen 1 hour from now or tonight or tomorrow or 5 days in the future, right? It's very similar to what we look for weather forecast every day. So we want to see if we can do the air quality forecast. So we put together all this data into model. And this is a model simulation of fires, again, those same fires which we looked earlier, 2017, in August and September. And this is a global model designed by NASA. It's basically a climate model, but it does provide air quality information as well. And it does include all the satellite data and some of the ground data as well. So there are three things the model is showing. One is smoke coming out of those fires over there, dust coming out over Saharan deserts in Africa, and then the blue colors. What is the blue color? Anyone? Sea salt. Yes, it's there, right? The scale is there. So sea salt. So we get a lot of particles emitted in the atmosphere by wind blowing over the ocean surface, right? And those are basically sea salt particles. They stays in the atmospheres and they moves all around. So you can see multiple hurricane system, Irma and Josh, and they are producing a lot of sea salt particles. And because of all those weather patterns, the smoke actually is trapped in some of those and moving to long distance. Similarly, the dust is actually along with those hurricane system actually moving all the way to the US. So we do get actually dust transported from the Saharan desert to east coast of US, and some pollution from the China over the western US. And at the same time, we also transport pollution and smoke all the way to the Europe from the US. So it all really depends on how the winds are, how the weather patterns are going at particular time. But these models are now being used globally to get a good idea about what is going to happen in future. So these are forecast model. Okay, so before I move on, I will show you a tool how to access all of this data. But any question? Yes. Yes. Yeah. So give me a minute. I'll show you how many fires are there in a.
Also in Alaska, I was talking to people in Alaska that said
Yeah.
Anchorage, there's fires all over the place. They didn't have rain. It's like what happened to us years ago.
Yeah. I'll show you a tool which will actually map the fires all over the world, and you can zoom in any area to see those fires. Any other questions? Anything else? No? Okay, so those who have their laptop or computer or on the phone, you can also look on the phone. So I want you to actually just go through this so that you have a good handle on what we're trying to do. So if you just Google on your phone search NASA Worldview, so if you just Google NASA Worldview, you will see this link, US DIS Worldview. And NASA Worldview. Were you able to get it? And if you click the first link, you will reach to this page, right? So this is a tool to display near real-time satellite data. There are like 600 different geophysical parameter which are available in almost near real time, which means anywhere from 15 minutes to 3 hours. And when you start, you will see a lot of examples are given actually here. So you have fires, tropical cyclones, sun glint, earth in the night, more fires, there's hurricane systems, all different kinds of examples are given there. So you can actually browse around and see. But before that, let me close this. Or maybe I can show you actually an example. So let's click on the first one, the satellite detection of fire. So these are pre-generated profiles of worldview which are created just to explain a specific air quality event. So this is specifically for fires. So once you click on that, you see a global picture, right? Now, do you see those red dots on the maps? Those are locations of the fires. And on the bottom left, if you see, this is from 2019, July 18. So this is July 18, 2019 data. And all those red dots are basically locations of places where satellite has detected the fire on that particular day. Okay. You can read little bit description on the right, but let's move on to the next. Click on the next. So this is zoomed into one of the fires. You can see the smoke coming out of that fires, and all those red dots are showing actually the location of the fires. Now you can see a pattern there, right? It does not mean there's no fire in that middle of those red dots. What happens is when the algorithm works, sometimes because of these thick smoke plumes, we cannot see underneath it. So sometimes there is a limitations of detection. So if there is a very thick plume of smoke, it's very hard to detect actually what is going on underneath of that. If you click next, you will see another way to look those fires. So this is called a comparison, right? So you have a image slider which can actually slide to different types of data layers. So again, left side is same thing which we were looking, the RGVs with the fire locations, and on the right side is a different combination of the band. It's not RGB, it's a different combination, and this combination is chosen specifically to see underneath those smoke. So if you look on the right, there are spots near those red dots which are basically burnt scarp. When fire is burning, so the land is actually very dark, and you can see that actually in this particular combination of spectral channels. So on this image, you cannot see those red scars on the land, but on this combination, you can see them. And that helps actually to calculate how much area on the land has burned because of certain fire. So we can actually estimate a specific square kilometer of the area which have been burned by individual fires. So this is the location in Portugal where there were fires. This is the same nighttime images I was showing earlier, again available through the worldview, and you can look at that. These are the fire location. You can see a lot of lights from those fires. This is a quantity called aerosol index. It's very similar to aerosol optical depth, which I was showing earlier. It does, red color shows very high values, and the orange color shows lower values. So again, you can see the smoke. Where there was smoke, the concentration of the particles in the atmosphere is high in this specific data layer. And in the last, this is individual fire very zoomed into that area. Okay, so let me just give you, this was just one case study which they have prepared already, but if you go back here and then click again, then it will basically take you to the today's date. So this is 2019 August 23. When you open the first time world view, it will always take you to today's date. And this is today's coverage of the satellite. You can see there are portion of the earth which are still not covered. And on the left side, there are multiple layers which you can display. So these are 3 base layers. These are coming from 3 different satellites. You can choose which one you want to display. If you click on that icon, then it will actually either hide that layer or it will open up another layer. So this is from Aqua, and this is the Weir satellite, which does not has that orbital gap because of the large swath. Now, if you want to zoom in to any area like Amazon, we were looking earlier, there were a lot of fires happening there. You can see the smoke and the cloud mix. And if you want to look at specific fires, then what you have to do is click on that add layers. Once you click on the add layers, a pop-up window will open with a lot of parameters in it. And you can choose which parameter you want to display. So we want to display the fires. So if I go in the fires, and again, inside the fire, there are many different variables. I want to just show the red dots or the fire anomalies or thermal anomalies, then it's fire and thermal anomalies. Once you click that, again, it will give you an option to choose which satellite you want to display. I'm going to just choose the Weirs, which is highest in resolution. It has daytime and nighttime. And once it is selected, those layer will be displayed on the map and they will come on the left side. Again, you can close particular layer. And so one more thing you might have noticed here in this specific case, this is from yesterday. You can see actually a lot more fires, and some of these fires are daytime fires and some of them are nighttime. So this is only nighttime fires. When I put the daytime also, then you will see a lot more area is actually burning. If you look entire globe, this is from yesterday again, and you can close this layer. It looks like entire world is burning, right? But it's not really. I mean, these are 400-meter resolution data put on the global scale. So that's why they will look like that. Even if you really zoom in here in a specific area, you will see it's not really that much. I mean, there are a lot of fires, but it's not that entire area is burning. So yeah. Yeah, so that's why. Yeah, so if or there could be a one large fire, but because of the resolution of satellite, it will point as like 10 different fires because it's really large. It cannot contain in one pixel satellite. Similarly, you can add other layers, and if you don't know actually what you want, you can just type the keywords here. Let's say I want to map the rainfall, right? So I don't know what parameter is that. I will just type rain rate, rainfall. So there are so many rainfall, surface rain rate. Let me find the one which I'm familiar with. the iMerge. So this is a global product, again, combination of multiple satellites, give you every 30 minutes rainfall all around the world. And let me close the fire layers. So now you can see where on the earth rain is happening all around the world. You can change the date here, go back in time. Unfortunately, you cannot go in future. The models will do that for you, not the satellite. So you can go back in time and see. And some of the data sets are as old as 20 years. So you have almost starting 2000, some of the data product. Not everything is that old, but some of that is that old, specifically for aerosol particles and fires. Sorry? It does have a parameter for dust, I believe. Means, yeah, so let's see, these are monthly. There's a satellite called AIRS, which provide some dust over ocean only, I think. Let me close this one. So you can see some dust score over Sahara, over some over here. But the other way to look dust is actually a dust are basically particles. So you can look the aerosol index. Dust specifically absorbs light in UV part of solar spectrum, and this specific parameter is designed to actually look dust and smoke. So if you click on the aerosol index, I'll choose this satellite. It has a better coverage. And let me close some of these layers, not to confuse. And you can move around these layers, okay? So if you are not able to see things properly, you can move them around. There's also layers to name the places, coastlines, things like that. So you can just drag those layers anywhere you want in that panel and they will come up. So right now put the aerosol index in the bottom and it should come up, and now I can see the boundaries. So this, you see this one over Sahara, high colors, red color, these are the dust actually. And this is the smoke coming out of the biomass burning. Similarly, you can see some high values over Arabian Peninsula. So all over wherever there is a desert, you can see some values over western US in California and Nevada in this area. You can see in Chile. So some of these are because of the smoke, some of these are because of the dust. So yeah, just play with it. There are so many severe storm, flood, vegetations, if you are interested in looking long term how things are changing around. And the vegetation data are very high resolution actually, up to 30-meter resolution. So you can see very small scale changes very quickly. Yes. So unfortunately, we cannot detect from the satellite whether they are who created them, whether they are natural or intentionally by human activities. The best resolution we get from the satellite is 30-meter. Yes, it is plenty, but that specific satellite which gives you 30 meters only gives once in a 15 days observation. The one which I'm showing here is every day, but it has a 375-meter resolution, about 400-meter. I mean, it is already there. The data is already there, and it goes to the people who are responsible for managing those forests, to the government and all. It goes. The data system is there. They get all the alert and everything. It's not that they don't know about those fires, but acting on that is beyond our control. Yeah. So unfortunately, we can provide the information, but acting on that information is beyond our control, or beyond our even we cannot even recommend that. Yeah, yeah. Any other questions? Yes.
So you may use data from satellites and try to compare them with some monitors, but these satellites that pass through a certain location twice a day or so. So when you do the analysis with monitors, you would want to compare the values at that given time, not okay. Yeah.
So the question is, because there are two types of satellite. One is geostationary, which giving you very frequent measurement every 10 minutes. So they are comparable to what your monitors are giving. So you can compare actually every time. One more thing to note down, actually, I don't know if you noticed that, but if there is a cloud, we cannot get any information about the particles. So we can only get information about particles from these passive sensors in cloud-free condition. If there is a snow on the surface, then also we cannot get any information. So for the polar orbiting satellite, which gives you only one observation in a day in cloud-free conditions, so usually on a global scale, there's 50% chance of cloud on any given time at any given location. So you have 40 to 50% only data available for particles on a given day on Earth. So when you compare with the ground monitor, we make sure that we only take measurement from the ground monitor at the time of satellite overpass at that location. So, and that we know very precisely what time satellite overpassed at particular locations. But there are other ways also. I mean, sometimes you make a daily average and compare with that as well. Depending on your application and what science question you are addressing, you can actually do different spatial and temporal averaging. Anybody else? Yes. So that is true. Water vapor is a greenhouse gas, and but it's naturally occurring, right? So it's not human induced or anything. So we are not worried about that, and it has a lot of variability. Sea salt particles are typically scattering type of particles. It means they reflect a lot of sunlight back to the space. So in effect, on a surface, they are providing more like a cooling effect. So in other words, you can say they're offsetting some of the warming which is happening. A lot of these aerosols actually which are scattering in nature like sulfate or sea salt, they do have a net cooling effect on the surface. Other aerosols like dust and smoke, they are absorbing in nature, so they have a net warming impact. So global estimates suggest that aerosol does offset some level of warming because of the greenhouse gas, but it's the quantitative numbers is very uncertain because we still don't understand a lot of things how these particles behaves. Okay, anybody else? Yeah. Mhm. Ah, yeah, yeah, yeah. No, I'm not familiar with that study actually, so I don't know actually what's happening there. Yeah, yeah. Okay, okay.
Some of the technologies used in our actual purple sensor to do obviously remote sensing. About that?
How that works?
Yeah.
Brandon, you want to explain that, how purple air sensor works?
Similar to what Pawan was saying, the satellites are optical devices, and they're purple air sensors. It has a small fan inside, so it's pulling air into the device. And then there's a small laser inside of there. That laser is going across the airstream. The particles are then reflecting light, and it has a photodiode that then measures that reflectance. And then it's actually counting the particles that pass through. And then it's transferring that into, it has a calculation that transfers it into mass. So it's an estimation of PM2.5 mass. So it's not actually measuring mass, it's making an estimate of it based on the particle count and the reflectance that it measures. They're the same exact sensors, they are identical, and they should measure the same. You can call them redundant. They can indicate if one's failing, potentially. You may have one that fails and they're not matching, and so that can provide an indication of whether a sensor has failed. Yeah, in the back.
So I think one of the issues with the sensors could be humidity in the air that can interfere with the measurements or something like that.
Yes. So when the reference method sensors, BAM or GRAIM, they make measurement, they are called, they measured something called dry mass, means in controlled conditions. So there are controls to control the relative humidity by heating the air samples, and it keeps about 40%, right? The relative humidity. Yeah. So, but in this purple air sensors or similar to other sensors, they don't have that mechanism to do that. So they are more ambient measurement rather than controlled conditions. So yes, the relative humidity will impact the measurement, specifically when relative humidity goes beyond 85%. Then it significantly increases the scatterings of particles, and that should change your. Yeah, that will give you a high concentration for the same dry mass. Is there any bias adjustment to these sensors? Not really, right?
There are some researchers that have done some corrections, and then Purple Air has actually put those on the map. I didn't show those because those corrections are based on alternative locations rather than the South Coast Air Basin. The raw sensor, the lifetime should be about 40,000 hours, but that's going to be dependent on the aerosols that are going through the sensor. So if it's mounted in a location where it's going to have a high impact of particulate matter, the lifetime will be reduced. $40,000 hours. The current data rate on the sensor is every 120 seconds. So every 2 minutes, you'll have a new data point being placed on the map and in the files. The question is how many bytes? I'm not, it's going to be text, so it's going to be small. I don't know what the actual bytes are. It'll be, At this point, it would be a replacement of the whole unit. Yeah, that's a good question. So to answer that, The best way to say it, the sensor does not differentiate between different species of dust. It just gives you counts for particles for 6 different sizes, and then it translates that into mass. And depending on the type of aerosol or dust that you have, it'll reflect differently. So as we saw those pictures from Powon, you had the very dark dust, and then you also had lighter dust, and you can imagine that that's going to reflect light differently, and so that would impact the performance of the sensor. And so we showed you some of those performance evaluation results. And so we've done evaluations here in the South Coast Air Basin. You can look at the results and how well it did over 2 months at the Rubidoux area. That's an inline site near Riverside. And then as well, we did laboratory studies where we challenged it with controlled temperature, relative humidity conditions, and then varied concentration as well, and challenged it that way.
So if we're measuring PM1, is there a possibility to put out the number concentration data instead of like just, I mean, I know that this is more like for air quality purposes, but is it possible to like put out the PM one number concentration?
Yeah, the number concentration is available. It's not going to be streamed real time onto the map, but you can find that in the secondary file that you download on the purpleair.com/sensor list. It'll have all the particle count information right there by columns.
So any other question related to sensors, people who already have on their use find anything? Anybody is looking the data on sensors? Any interesting thing you find? Yeah, go.
Yeah, after I hooked it up, I was just curious how sensitive it was. Like if I use my barbecue versus my neighbor uses theirs, and you can see it, and at different times of the year with things coming off the trees, and that as the wind picks up, you see it immediately. You can look on your phone. So how it compares to, one of the $100,000 rigs, I don't know, but just intuitively, you see in real time, turning on the dryer, turning the soil, mowing the lawn, this type of thing. You see an anomaly right away.
Want to share any experience? So in this project, one thing we want to do is we want to hear all these stories. Also, if you, I think Olga is already probably asking that, but if you can send us picture where you have mounted the sensor, that will be really great, will help us in our project for presentation and for reports purpose. If you can send with yourself or somebody who's operating, that will be much more preferable. Uh, Yes, and if you find things like what you're saying, or if you are making artificial changes in the concentration, if you can keep that log somehow, and if you can get, it will help us when we start analyzing the data in a volume like that, like small peaks, because those data most likely we don't want to use for the other analysis, and we are comparing with other data sets. So any other kind of help you need, feel free to email us, I think, or if you want to learn more about the satellite data, I mean, there's a lot. I just showed you one tool, but there's plenty of the things available. All of the satellite data are free for anyone to use, to download for any purpose you want. And they are available in nicely designed tools, which you can access on your phone even nowadays. So, yes.
You gave us the site website. AQMD has a website devoted that we can access, and then, is that correct? No, for our citizen scientist stuff.
Yeah, so So right now it's just purple air, right? So is there any dedicated website
Oh, y- Mhm. Yeah, us, primarily, like, I've been communicating, so feel free to send me pictures, questions, notes. So on the, like, we will be, posting updates on the project websites. If something is happening in our area, I will be sending you emails. But yeah, feel free to contact me.
website where most of the steps are there. There's also, I think, forum there where you can put comments and post things, and all the contact information.
Just want to say about a year or two ago, there was a meeting with CARB, and we had a fellow that was talking about citizen scientists. I don't remember who it was, but there's something that's going on. Anyway, he did say that one of the first citizen scientists was Charles Darwin. So we're in good company.
Sam? So Ashley will be. Thank you. Yeah. So so I'll email it. Email it out. Yeah. Eventually. Yeah. Yeah. Any more questions? Last chance.
Any other comments, questions, or any feedback, or you want us to do things differently? Any other comments, questions, or anything you want us to do things differently, or any suggestions? Um, and if you have friends, family actually who wants to install one of this sensor, feel free to contact us. It will depends on where they are located, because right now what we're trying to do is trying to match the satellite grid points with the sensor locations, and we have done distribution according to that. But share with us. Olga has a registration page where they can submit their information, and then we can go from there. Right. Okay. No questions. So I think before we leave, can we do a group picture? Where should we do? Here or outside? Okay.
All right. So thank you very much, everyone, for coming. We're gonna go outside to take a picture. For the people who are on the web, this concludes our workshop for today. Thank you very much for participating, the remote participants and people in this room. And stay in touch. Thank you.